Hi, welcome to Statics CVEN 2301. I'm your professor, Dr. Annette Hernandez.
And this is my avatar. So let's get started.
At the end of this chapter, you will be able to explain mechanics or statics, what they study, the different types of units in terms of SI or US customary. You should be able to round your answers appropriately along with appropriate significant figures. And finally, you will learn a methodology for solving problems. Mechanics is a study of what happens to a body when you apply a force. That force can be either tensile or compressive. It can be large or small. This course focuses on external forces upon a rigid body. Mechanics is the study of what happens to a body when external forces are acting upon it. It can be divided into three subsections. One is rigid body mechanics, the second is deformable body mechanics, and the third is fluid mechanics. Rigid body mechanics can be divided further into two separate course materials. The first is statics. This is when a body is at rest. The second is dynamics, when the body is moving. Fluids build upon statics and dynamics and focuses on both incompressible and compressible bodies. The difference between fluids and rigid bodies or deformable bodies is that the bodies that it deals with takes the shape of the container that it is in. In this course, our focus will be on rigid body mechanics, specifically statics. These are some fundamental concepts that you'll be seeing throughout the study of statics. So the basic quantities or dimensions that we'll be working with are length, mass, time, and force. Time, not so much because that's associated with movement. We're going to idealize the systems that we analyze in this class. This just means that we're going to simplify the system. And so, for instance, a particle has mass, but in our analysis, we're going to neglect the size. We can do this because whether we are looking at a person, a car, a house, or a huge building or a bridge, it is basically a point relative to the Earth. So that way we don't have to worry about the geometry of the body. Furthermore, we're going to look at rigid bodies, meaning that the particles stay the same distance from each other, never changing, and so we don't need to worry about the materials. We'll learn about that in other classes like solids. And lastly, we're going to look at concentrated forces to begin with. That just is a load at a particular point, that point being small enough. It could be an area, but it is small enough relative to the rest of the body that we can think of it as a point. We will also be using Newton's laws of motion, the first of which states that a particle in motion or not in motion stays at that state if it's in equilibrium. The second law, or Newton's second law, is that if a particle is acted upon by an external force, then it'll increase in acceleration. And that may be an increase actually or decrease, so acceleration or deceleration. Newton's third law states that for a particle in equilibrium, for every action, there is an equal, opposite, and collinear reaction. Finally, Newton's law of gravitational attraction is about the attraction between any two particles. And simply stated, it is the force between the particles is equal to the universal gravitational constant times the mass of one particle times the mass of the second particle divided by the distance between the particles squared. If we say that the universal gravitational constant times the larger mass divided by r squared, where the larger mass is equal to the mass of the Earth, is equal to the local gravitational constant, or little g, then this becomes the force is equal to the mass times the local gravitation. That local gravitation constant for most engineering calculations is set at sea level and a latitude of 45 degrees. That is what we consider standard location for engineering calculations. We talked about our quantities, and we know that they are related by Newton's second law, which is the force is equal to the mass times the gravitational acceleration. So depending on which system you are using, whether that's the international system or SI versus US customary, three of those units are base units, and the fourth is derived. So if you look at the international system, or the SI, then you measure mass. So if you were to weigh on a scale, you would get kilograms or grams. You measure mass, which means it's a base unit, and then you can calculate the weight. If you look at US customary and you scale or you measure something on a scale, let's say you step on a scale and measure yourself, you're actually measuring weight. So weight is a base unit, and then you can derive out the mass. In the International System of Units, suppose we measure mass at standard location, and suppose that mass weighs 1 kilogram. That 1 kilogram subjected to a local gravitational constant of 9.81 meters per second squared would result in a weight of 1 times 9.81 or 9.81 kilogram meter per second squared, which gives us 9.81 newtons. On the other hand, suppose we're using US customary and we measure weight at standard location. And let's suppose that the weight we measure is 32.2 pounds. When 32.2 pounds was subjected to 32.2 feet per second squared, then that gives us 32.2 divided by 32.2, or 1 slug. And slug is the mass associated with 32.2 pounds. Listed here are the units associated with each one of the dimensions per system. So we have the US customary system, or the foot-pound second, or FPS, and we also have the International System of Units, or SI units. The dimensions are listed across the top, so length, time, mass, force, and the units are what give the dimensions magnitude, and they're listed in the table. Again, notice that the asterisk here denotes a unit that is derived. So again, you would measure a force, and then you would derive slug in the FPS, or US customary, and you'd measure mass and derive force in the SI units. We will focus a lot on using the International System of Units, or SI, because this is supposed to be a worldwide standard. So we're going to talk a little bit about the rules required to use the SI system. So first of all, there are no plurals. If you have 5 kilograms, you do not put an S at the end because that looks too much like kilogram second. Also, you should separate your units by a dot. And that's if, of course, they're either both in the numerator or both in the denominator. So here I have the example of a meter second, and it should be m.s. Most of your symbols are going to be lowercase. There are exceptions that you will see, and that is a capital N for Newton and your pascals, or capital PA. M and G stand for mega and giga. Mega and giga are prefixes that you will be using in the SI system. When you're looking at exponential powers, they apply to the entire unit. So cm squared, for instance, is not centa and then your meters are squared. The whole thing is centimeters squared. So centimeter times centimeter. Lastly, you should not be using compound prefixes. Let's say that you are multiplying two sides of a square. One is given in meters and the other is given in centimeters. You do not multiply and then present your results in meter, centimeter. You should actually convert either the centimeter or the meter to the other unit, and then use either centimeter squared or meter squared. Listed here are common prefixes used in the SI system. You may also see C, which would be centi, and that's 10 to the power of negative 2. And the submultiple would be 0.01. Or you could possibly see deci, and that is 10 to the negative 1. And the SI symbol is a lowercase d. As you are calculating, there are several checks you should also keep in mind. The first, the very most important check is Your equation should have dimensional homogeneity. That means that the dimensions on the left-hand side must be equal to the dimensions on the right-hand side. Furthermore, every additive term on the right-hand side or on the dependent side must also have the same dimensions. Make sure that you use the correct number of significant figures. In engineering calculations, typically you want 3 significant figures, and this is because it matches up with the ability to make measurements. So for instance, if you have a ruler, there's no way that you can have 4 significant figures. Let's say you have 3¼ inch with a little bit more than a quarter. You cannot, with any accuracy, measure 3.256, but you can approximate 3.25. So 3 is typical of engineering calculations. But when you're doing the intermediate calculations, I would keep whatever significant figures are given. I would make my calculations and I would not do any rounding until my final answer. And at that point, then I'd have 3. This is because, let's say your answer is 3.253, and then you multiply that by 10, and then you divide by 2 and multiply by 100. At the very end, if you have cut off that last digit, you might end up making significant magnitudes of error on that answer. Therefore, you keep your intermediate calculations, and then your final answer will take 3 significant figures. Some of the ways we count significant figures, of course, listed here. Every non-zero digit is always significant. If you have zeros between non-zero digits, those are significant. Any leading zeros are not significant, even if you have a decimal. So 0.0053 only has 2 significant figures. It does not have 4. And trailing zeros, of course, are significant for decimals. So if you have 0.12000, then you have 5 significant figures. The last 3 are actually mathematically correct, but it's not something that we really have to consider. That is constants. You don't need to worry about how many significant figures are there. You just use as many as you need. Exact numbers like 1, 2, 3, 4 have an infinite number of significant figures. And that leads to the trailing zeros in a whole number may or may not be significant. So if it's an exact whole number, then it is significant. When you're rounding off, this is based on the law of averages. So if you have a number that's greater than 5, then you're going to round up. If you have a number that's smaller than 5, then you're going to round down. If your number is equal to 5, so if you have 0.035, then because the preceding number is odd, you would round up. That would be equal to 0.04. But if you have an even number like 0.025, then you don't round. That becomes 0.02. So it depends on whether it's even or odd. To demonstrate the problem-solving methodology that I like to teach students, I'm going to work problem 1-19 in Hibbler, the 15th edition. So the problem statement is that the specific weight in weight per volume of brass is 520 pounds per cubic foot, and we want to determine its density or the mass per volume in SI units, and we need to use appropriate prefix. Step 1 is to write the problem statement, or what are you looking for? That doesn't mean to rewrite the problem, just what are you looking for? In this case, we're looking for the density of brass. Density is given the variable rho. So rho of brass is equal to what in SI units? Step 2 is, what are you given? And so in this case, we're given the specific weight. The variable for specific weight is gamma. So the specific weight of brass is equal to 520 pounds per cubic foot. Next, we want to write all the equations and assumptions that we need to solve our problem. So let's begin with the governing equation. Our most basic building block, that is that the weight is equal to the mass times the gravity. If we divide both sides by volume, then we get weight per volume is equal to mass times gravity per volume. It's important to realize that this case, weight per volume is just the specific weight, or what we were given. And mass per volume is the density. That's what we're determining. In other words, gamma is equal to rho times gravity, or density is equal to gamma divided by gravity. Next, we want to write our assumptions and our knowns. We're going to assume the gravity is 9.81 meters per second squared, or at standard location, the gravity in SI units. For every foot, we have 0.3048 meters. 1 pound is equal to 4.448 newtons, and 1 newton is 1 kilogram meter per second squared. So once we have our equations and our assumptions, we can begin to solve our problem. So we start first by solving for our density. That is the specific weight divided by gravity. So we have 520 pounds per cubic foot divided by 9.81 meters per second squared. Then the rest of this is just conversion from our US customary into our SI system. So that's 4.448 newtons per pound times 1 foot per 0.3048 meters, the entire quantity cubed. And then we also want to take our newton and change it into kilogram meter per second squared. You can see here that everything will cancel out except for kilogram per cubic meter. Solving for density then, that gives us 8,326.3 kilograms per cubic meter. Now again, we only want this to be in 3 significant figures for engineering calculations. So let's first change this into scientific notation. That is 8.3263 times 10 to the third kilograms per cubic meter. Since we are only wanting 3 significant figures, then we have to round the third figure. So we get 8.33 megagrams per cubic meter. Now for discussion, we want to determine if that is a typical answer. So I just go into Copilot and say, is 8.33 megagrams per cubic meter a typical value for the density of brass? And here it says, sure enough, that the typical density of brass is 8.2 to 8.7 megagrams per cubic meter. So you can take that and you can write that as part of your discussion. The discussion here is where you look at your answer and determine whether it's a typical value or whether it makes sense, or maybe something interesting about the problem or something interesting about the solution method, or even where maybe there could be errors in your calculations. So in this case, you can even just Google. You don't have to use Copilot and say, is this typical, or what's something interesting? That would go here in your discussion section. And that's one method for solving problems in this course.